Okay, guys, I want to do just one problem uh, for more circle so that you can understand that I realize that you might be visualizing it always on the positive side, like what I shown in class. But it is important to understand it can move anywhere. Okay, it can slide left and right along that horizontal axis. So we're going to do one problem now. That's problem. Oops. Okay, so it's problem 951. Okay, and it's very simple. In the book, you have this state of stress at some point in the body that looks like this. We have the shear that way. And I'm going to erase this problem thing because we don't really care. I need space. And we have a normal one, normal force that looks like this. And I'm going to label them thinner. This one is 80 megapascal. It looks like 86, but it's not. It's 80 megapascal. And so this is 82 also, and this is 60 megapascal. Okay, the shear. Okay, and so what are the first steps? What do we need to do first? The very first thing we need to do is immediately write down what is what. So we have that our sigma, these are the x's, this is x, and this is y. And so our sigma x is equal to, there's nothing in the x direction, so it's 0. Sigma y is equal to minus 80 megapascals, and tau xy is equal to 60 megapascals. And so the first step we said we need to do is to calculate, to start drawing the Mohr circle, is to calculate the sigma average. Oops. Sigma average, because we said that the center of the circle C has coordinates sigma average, comma, 0. So this is a horizontal, this is a vertical coordinate. And now I'm going to draw the line like this, and I'm going to draw the vertical line like that. And we said the vertical is positive downwards, so that's our shear stress. And this one is positive to the right, and that's our normal stress. And C is somewhere on this horizontal line, and it's the amount you start measuring. This is positive, that's negative, so it could have negative values. Sigma average would be an average between the sigma x and sigma y, so it's sigma x plus sigma y over 2, and that's equal to 0 minus 80 over 2 ends up being minus 40. So already we're not having such a great time because we are having this negative value, right? And so I'm going to measure something like, let's say, put it right here. I know it's going, so I know I'm going to put it right here. That's negative 40. And I'm going to write here negative 40. So don't write it directly below. Remember, it's going to be vertical lines and horizontal lines. So always write in corner. Anticipate. Okay. So that's minus 40. That's my C. And I'll label it here. Okay, so we got the C. So what's the next step? The next thing, if you remember, when we had a circle, we had to construct a triangle. I'm going to draw the circle for you. So it looks like this. That's the location of sigma average. This is the axis, right? We did it all the way on the right. It doesn't have to be. But just because we needed to draw the circle, we know that the point is going to be somewhere here, supposedly, right? And this is a circular, so it's a smaller circle. All right, so this is no good. Let me redo it. That's the circle. And we said it's somewhere here. That's the point we're trying to find. And we said that this triangle we know how to find because we have the location of this. We calculated that sigma average, right, from the axis. So that's sigma average. That's why I recommend you draw this circle for yourself. The finished one that I drew to you in the lecture, you have to draw it too for yourself in your cheat sheets. And then this amount here, this vertical position for the triangle, that's the triangle, okay? The vertical position is equal to tau xy. But we also need to find this bit here. And we said that that's sigma x minus sigma y over 2. And so how much is sigma x minus sigma y over 2 is equal to 0 minus 80 over 2, and it's equal to 40, plus 40. Okay, so that means minus would be in this direction. But what we have is plus, it's in that direction. So now we have a C here. The plus 40 will be right there, going in this direction, ending right there. So actually, this point here is that point here for us, okay? And then from that point vertically down, we measure tau xy if it's positive. In our case, it is positive, so we measure 60. So this is 40, so it's about that much more. So that will be 40, and then a little half that, about here, that will be 60. Okay, so this amount here, I'm going to go far because I don't know where this is going. This is 60. Okay, and so now we have this triangle, and it looks like this. And what do we say about that point? I'll call this point A. That's our reference point, remember? And the reference point, I'm going to draw this thicker, this line. There. And so now we have that line, and we know that that's our radius. And I'm going to mark it as R. And so of the circle, right? So let's just calculate what that radius is. So R would be, so we know how to draw the circle, but we need this, and I'm going to shade it because that's the stuff that gives us, this is 40, this is 60. And that's the stuff that gives us all the information about this problem, okay? So R is equal to square root of what? 40 square plus 60 square. So it's 40 square plus 60 square, and that means 72.11 megapascals. And now we can construct the circle. So now we're drawing the circle, and that's not so easy. So I'm going to draw a line vertically here so that I know it's going to go somewhere here. And this line is parallel to that line. All right, doesn't look so good, but okay, that's the best I can do in these circumstances. Maybe I can make this a little better down here. Okay, that looks good. And so now we have our circle. And so what we can calculate now is we are asked to calculate both the principal stresses and the maximum in plane shear stress. And we said, I'm going to use a different color. We said the principal stresses are these 2 points here on the horizontal axis. And so the greater one, by magnitude, not by sign, will be which one? What is the value here? This is a 0 here, remember? This is the axis, tau, and this is the axis, sigma. So 0 is here. So this amount here is how much? If the radius is 72.11, so 72.11 is from here to there, minus 40, right? So this amount here would be, I'll call that one of the sigmas, I'm not going to put in a letter yet, is equal to 72.11 minus 40, and that's going to be equal to plus 32.11 megapascals. And this other guy, I'm not going to put an index down, subscript just yet, is going to be equal, the amount is from here to there. We know that this is 40, and we know that from here to the apex is the radius, so it's 40 plus 60 is 100, but it's negative, this is negative, so it will be negative 100 megapascals. This is plus, this is minus, it doesn't matter, but we'll call the principal stress, which is the largest by magnitude, is this one, so that's a sigma 1 and that's a sigma 2. So sigma 1 is compressive, sigma 2 is tensile. But by magnitude, this one's larger, okay? So these are all our principal stresses. Now we want to calculate the maximum shear, in-plane shear stress. And we said where the circle cuts the horizontal axis, that's the principal stresses. And for that situation, tau is 0. But now I'm going to use a different pen to make sure you don't mix it up. For these 2 points, we said that these 2 points, either one, mark what? The maximum shear stress. So tau maximum in plane is equal to what? It's going to be equal to from here to there, so that's the amount, that's exactly the radius. So it's equal to R, which is 72.11 megapascals. Okay? And we know that at the same time there is a normal stress, which is the average stress, and we already have that. We calculated is minus 40 megapascals. So we've now described both the principal, the orientation of the principal stresses and the orientation of the plane of the element, the infinitesimal element, or the stress element, in which we have the maximum shear stress. And now the key thing is to learn how to redraw this, reorient them for these 2 cases. Do not attempt to try to draw these both on the same case, because they're not. This is one orientation, that's another one. This orientation has an angle theta s, and this orientation has an angle theta p for principal, theta s for shear, okay? And so how do we do that? Well, we have to calculate the theta p and the theta s. So what do we have for theta p? We have a formula, right? We have a formula. It's a tan of this angle theta, and I've shown you the slide that shows both of these side by side, the key formulas. Please look at it, please write it down, copy it onto your cheat sheet. And it tells you how to calculate tan. So the tan of 2 theta p, remember 2 is equal to 2 tau xy over sigma x minus sigma y, okay? And when you calculate that, you get that the smaller of the 2 angles, theta p, is equal 28.2 degrees, and that's positive. That means it's counterclockwise. But remember what we said when we're measuring the angle on the Morse circle, on the element here, when we rotate the element, we use theta. But when we're drawing it on the Morse circle, we use 2 theta. And so our rotation would look something like this. for the green points, we start from the reference line, right, the CA, and we measure about, this looks like it's maybe 60 degrees. So twice 20, this is a little less than 60 degrees. So it will come to somewhere here under this line, and it will be going that way. And so that orientation is to, I'm going to draw it like this, to theta P. And then the other one, oops, I was wrong. I lost track where I'm going, so I have to redo this. I think I'm going to redo it like this. It actually goes, look at the numbers, 2 tau xy over sigma x minus sigma y, and that's exactly equal to this over that. So it's 40 over 60, and it's minus, okay? And no, I'm sorry, it's a plus. It's just 40 over 60 because both are no. 40 over 60, it doesn't matter. We just need the angle, okay? So it's this way, and so it falls directly on top. That's what I really should have done. Now I have to delete all this. And of course it doesn't want to do it, so let me do it. Okay. So we have that this is to theta 1, I mean theta P, okay? And then the shading remains. There. So we're good. Now, so that's 2 theta P, okay, in that direction, and that's equal to 40 over 60, and that gives us this number. The next thing we need to do is to do the same for the theta S. And if you remember, the formula is slightly different, so it's tan of 2 theta S is equal to negative, and then you flip them. Minus sigma x minus sigma y over 2 tau xy. And that's equal to 60 over 40, right? And from that, I've switched everything around. I apologize. So I don't know how I could say 40. I'm mixing up the P and the S constantly without thinking. Let's just calculate. Let's just calculate it. 2 tau x, so 2 tau xy, so it's 120 divided by sigma x minus sigma y. Sigma x minus sigma y. So that's plus. So that's 80. And that gives you 120 over 80 is 60 over 40. So that's what we have, 60 over 40, and that gives us this angle. So that's the theta P. And then for theta S, we have 40 over 60, okay? Sorry about the confusion. So that's 40 over 60. It's literally opposite from what we have, right? So it's minus 40 over 60, negative that, and it would end up being theta S is equal to minus, so this would be happening clockwise, okay? And that's negative, so it's minus 16.8 degrees. And just so that I don't confuse you, I suppose I shouldn't write such silly things. I should really substitute dutifully the whole numbers. So this would be equal to minus sigma x minus sigma y. So that's minus 0 minus 80, right? Over 2 times 60, which is 120. And we see that the number is, this is negative, negative, so it's positive, 80 over 120, but negative in front. So it's negative 80 over 120. And when you sort that out, you get a negative angle here. Okay, so let's just keep it clean. And so these are the angles. So the sigma s is negative, okay? And if you look, it goes like that. So you see this one goes to the green point, this one goes to that. So from the reference line, this amount of angle here that angle is theta p, and the other angle from A to this point, that's 2 theta s. So now all we have left is these are the angles. Now we remember you need to half this angle to get a theta s and half that angle to get a theta p. And we're going to use those two angles to rotate this piece, this stress element in the proper direction to get to draw the principal axis and to draw the axis for which a tau is maximum. So for that, I'm going to now again switch to green, and hopefully I will find some space here so I don't have to start a new page. So this is the original element, and now it needs to rotate counterclockwise in positive direction by this amount, 28.2. So it's going to look something like this. It's going to look like this. That's your x-axis, and then from there you draw an angle that goes like this. That's 28.2, and that's your theta p. Okay, and that's the angle in which you have sigma 1 and sigma 2. Okay, so I'm going to first draw the element. Remember, so now you draw a face on that, and then the other face is perpendicular to that, and that's how you get your element. So this is now the proper orientation of your element, right? And all you have to do now is you draw with a, if you can make it thicker, that'd be good. This is this orientation here, okay, is the 32. Because when you rotate positively, you get to this point. So that's the 32, okay? And it is positive. And then the other one is negative. So it points into the face. And so I'm going to use now a thinner pen and write, oops, the values. And the values are, this is, what do we say? This is 32.11 megapascal. And this is also 32.11. And this one is 100 megapascal. 100. And there is no shear here, okay? So this is the situation for the P, for principal axis. Now we have to draw a different element for the orientation for the tau max. And now we have a slightly different situation. We have slightly different situation, and to be honest, I don't know where to draw it. I think I'm gonna erase this picture here so that I can keep all the values, okay? So let me see if I can do that. And that's the purple I need. And so I'm going to do the same thing as here, only again I first draw a horizontal line kind of on the right side from where I know my picture will be, and then now I draw the angle down, and it's slightly smaller than this angle. It's this angle here. See, because here we're going down in the clockwise direction, And so in that direction, I'm going to draw an angle. It's slightly smaller than that, so it's going to look like this. Sorry. That angle is theta s is equal to minus 16.8 degrees. Okay? And so now I have that. I can now draw the face on that that's perpendicular to that. And then the two other faces that are perpendicular to that. And then another face that's perpendicular to them or parallel with this one. And now I can start using a thicker pen to draw my forces, my stresses, my stress state. Remember, that's the stress state for maximum shear, maximum in-plane shear, okay? And so how does it look? Well, again, it's in this direction, and we get that the maximum one is positive 72.11. And we said it would be going, if it's positive, it goes in the first quadrant. So for this guy, the first quadrant is this, right? Okay, and we have the average stress, which now we have to draw in all directions, right? Because it's in all four directions, both in X and in Y. And it would be, we calculated that it's negative, so that means it's pointing in. It's really along that axis, so I should have drawn that correctly. Okay. And because I didn't, I'm going to make sure I do it right. So I'll kind of erase this. There, that's better. And now I'm going to redraw the line that I threw away, which is this one. That's how I got this. That's the angle, okay? And it's going down, so it's negative. Okay, and so let's write the values. The values, these, all the normal ones are the average, which is minus 40. So this is minus 40 megapascal. And then I'm going to write here minus 40, minus 40, and minus 40. Okay, and then the shear, I'm just going to write in one corner, is 72.1, and it's positive, right? So it's 72.1. Okay, so this is our principle, and since you're not going to have different pens, what I want you to do is I want you to write, when you're doing the principle, this will be a separate part and you will have a title, principle. And then under that, the whole work with this picture. And then somewhere a little further away, not piled up on top because it needs to make sense that it's all together, you will write maximum in-plane shear stress. And these would be together with that, okay? All right, so that's how it works. So please note that you can have, depending on what kind of sigma x, sigma y, and tau xy you have, you can have this circle be completely on the negative side without even cutting into the positive. So be really careful about your signs. Follow these equations religiously, and remember that the positive sigma axis is to the right, negative is to the left. Positive tau axis is down, and negative is up. All right, so pay attention.